Okay, we're now recording. Okay, welcome everyone. So this is the last class for this term. And today we're going to talk about positive feedback. So this is chapter 23. Let me just do one thing. I need to just send one quick email to somebody else so they know. Hold on for a sec. Okay. Okay, good. Okay, that's it. Okay, so we're going to talk about positive feedback. So this is chapter 23, and what we've got here, shall I expand it a bit? So this is a little genetic circuit. People have made these genetic circuits. These ones produce a protein X, and X activates the production of itself. Okay, so this is an example of positive feedback. With negative feedback, X would repress the production of itself, but this is positive feedback. And positive feedback gives you completely new properties that are separate from negative feedback. And you can imagine something like this might be unstable. You know, the more X we make, the more X we make, and so on forever. It doesn't quite work out that way, as we'll see. So what kind of model might we construct to mimic this feedback system? So let me see, there we go. So I'm just going to put, for the degradation step V2, I'm just going to put a simple first order mass action rate law, okay, K3 times X. For the positive feedback, I'm going to use a Hill-like equation. All right, so it's a Hill-like equation, and I'm raising the X to the power of 4. And what that does, that gives it a nice steep slope on the positive feedback response. I just got two constants here, K1 and K2, and then this B stands for basal rate. It means I don't have a zero rate. I don't start off at a zero rate, but I start off at some finite rate. It just makes the graphs look better. That's all. And in reality, there'll always be a
Dr. Starro, do you want us to be able to see your screen?
Most of these genetic circuits, they leak because the inhibition is not, or the activation is not perfect. Okay, so I've got a little simulation here. All right, so if I bring this up, if you have any questions, don't hesitate to. We don't see your screen. Oh, really? Oh, hold on. Why don't you see my screen? Oh, here we go. Sorry about that. Better start again, hadn't we? Okay. Good, I'm glad somebody told me. So what we're going to do today is chapter 23. We're going to do positive feedback. And here's a little example of a positive feedback. X activates its own production, okay? So we have a gene here, V1, produces protein X, and X activates its own production. X then degrades at a rate V2. All right, and there's an inducer here as well. So these situations are unstable. You can imagine, as we produce more X, we produce more X and so on. But as I mentioned before, it doesn't always work out that way, as we'll see. So what are the rate laws? These are the rate laws I just mentioned, but they weren't on the screen for you to see. I have here simple mass action rate law for V2, and I have this Hill-like equation, but for repression rather than activation for V1, and I have a basal rate here, B, which basically lifts everything from 0. I'm raising X to the power of 4. That gives it, that gives the response a fairly sharp change, a steep slope. Okay, so that gives it a sharp response, which is what I need. Let me just check the messages. I want to check, how can I do this? I want to make sure that, come on, I want to see if there's any more messages. Okay, so you can see the screen now, I assume. All right. So let me go back to sharing. Okay. All right, so what I've got here, I've got this little simulation. I don't know if you can see this. Maybe I should expand the font a little bit. Here we go. Okay, so I've got this model here. So let me let me make this a bit tidier. So it's the same model as we had in that diagram. I'm producing X at a rate of this rate. 0.1 is the basal rate. I've got X to the power of 4, X to the power of 4. Okay, that's that hill-like equation. And then here I've just got x being degraded into, I'm calling something waste, but that's fixed at a rate k3 times x. And I've set up some parameter values here. So what I'm going to do is I'm going to do a simulation where I'm going to run multiple simulations at different starting points. So x is my initial condition for x. It's set at 0.05. Then I'm going to run a simulation. Okay, so maybe let's just do that first, shall we? So I'll comment all that out and then just run this. Come on. Oh, there's no plotting going on, of course. Let me run that. Okay, and I get something that looks like that. Not terribly interesting. But what I'm now going to do is I'm going to run 20 simulations. All right, and each time I'm going to change x a little bit. All right, so well, I'm going to have a different x each time I go around the loop, and each time I go around the loop, I'm going to do the simulation. And then what I'm doing here is I'm just stacking up all the results into one big matrix M1, and then I'm just going to plot the whole thing. All right, so if I run this, you will see something like this. So the x-axis is time, y-axis is x, and you can see I'm starting x at many different conditions. There's 20 of them. And the thing you should notice is that some of them, the low ones, end up at a low steady state, and the higher ones end up at a sort of higher steady state. So this system actually has two steady states, a low state and a high state. All right. Now, what I can do here as well, I can make this a little bit finer. Let's see. Okay, so now you can see instead of going from 0 to 3.5, I'm going from 0 to 1.75. And you can see there's a middle one here that seems to take much longer to reach the high steady state. Let me see if I can make that even more. I don't know if I can. Let's see. Make it even finer. Not quite. Let's go a bit more. No, let's try 60. Nope. Oh, I need to go much more then. So this is only reaching the lower steady state. Okay, so these are now 160 trajectories, and you can see that somewhere in the middle there seems to be trajectories that take a long time. They either take a long time to reach the high state or take a long time to reach the low state. And the reason for that is that there's in fact an unstable steady state right in the middle. Okay, and I can try and find that. In fact, let me see if I can find it. Actually, I probably need to go to a different. Yeah, so let's see if we can find, there are actually three steady states here. There's a high one, a low one, and there's a middle unstable one. Let's see if we can find that middle one. And what I've got here is another script I did, same model, same parameters. And this time what I'm doing is I'm going to calculate the steady state for different random initial conditions. Okay, so let me comment this out first. So I'm going to ask it to compute the steady state 20 times, and I'm going to start the x value at a different value each time. All right, then I'll print out the steady state value of x. So let's do that. So these are all steady state values. So if you look carefully, you'll see there's actually three here. There's one steady state at 0.144, there's one at 1.395, and there's another at 0.68. Okay. Now, if you've got any questions, do stop me, because I can't see you, so I don't know if there are lots of frowns or not in the audience or not. But do speak up if you want me to slow down or explain something in more detail. So all I've done here, I'll say it again, all I've done here, I've asked it to compute the steady state 20 times. And each time I'm starting the search at a different random point, okay? So you can imagine the Newton-Raphson here has been asked to start at a different point each time. And sometimes it'll reach this steady state. Sometimes it reaches this steady state. Sometimes it reaches this steady state. So there's actually three steady states here. So now what I'm going to do is uncomment these. Okay. Oops, sorry, uncomment them. Let's try again. Okay, there we go. What I've done is I've extracted the steady state, the 3 steady states. There's 1, there's 2, there's 3, okay? And I don't probably need to call this steady state here because already a steady state. But then I'm going to actually compute the eigenvalues in each case. So let me run this. And now you see for the steady state at 1.3095, the eigenvalue is minus 0.46. So that means this one is stable. The 0.68, sorry, the 0.1477, that also has a negative eigenvalue. That corresponds to the stable state as well. And then this one here, the 0.682, which is sort of in between the 1.3 and the 1.144, has a positive eigenvalue, and that shows you that this is unstable. All right. Now, if you ever messed with a toggle light switch, let me see if I can find a picture of a toggle light switch. Toggle light switch. Yeah, here we go. So this thing here, this picture here, which comes up any minute now, there we go. This thing here, okay, is actually a system that has 3 steady states. So you can see at the moment, the switch is down. So you could consider this to be the low steady state. If I push it hard enough, I can flick it to the high steady state where the switch is on. And if I'm, because this thing is spring loaded, and if I'm really careful, I can position the switch right in the middle. And if I balance it carefully, it'll sit in the middle and be neither on or off. That state is very sensitive. I only have to touch it lightly and it'll flick either on or off. Now, such systems like this, which have multiple steady states, in this case, 2 stable ones, are called bistable systems. All right, so these things are called bistable systems. Okay, they're called bistable. There we go, bistable systems. Very common in nature, very common in cells. They're often used to switch states from a low state to a high state. It's probably used, well, we know it's used a lot in differentiation. So when you want to differentiate from, you know, a stem cell wants to differentiate to a particular organ state, say a muscle, nerve, or whatever, there are bistable switches that operate, that flip the cell type from one cell type to another, okay? So these are actually quite common in nature. So what can we do from the point of view of theory? I mean, what are the conditions under which we'll get bistability? Okay, so this is what I want to look at now. So these are just the graphs we just plotted. Yeah, let me switch to the camera, and let me do some drawing here. So let me just make sure it's here. Okay, can you see all that now? Hope you can. So what I had was this unstable system, which I had activation of the gene by X, and I call that V1, call that V2. I can do a plot here where I can plot on the y-axis V1 and V2, and on the x-axis plot X. Okay. Now, since V2 was K3 times X, if I plot V2 against X, I just get a straight line. Okay. And the slope of that line is K3. All right. Now, what about plotting V1? Well, V1 looked like this, was this sort of hill-like function. It didn't start off at 0. So when X was 0, it started just above 0 at the basal rate. And then what it did this sigmoid shape. Okay, it's just an inverted sigmoid shape and did something like that. All right. Now, these points where they cross, these lines where they cross, is where the rates are equal. Okay, and of course, where the rates are equal, these must correspond to the steady state. So we'll see we have one steady state here, one steady state here, one steady state here. All right. I'm going to extend this line here to label these so you know which curve is which. All right. So imagine you're sitting here, okay, and I displace X. Okay, so I'm sitting on this steady state, and let's say I displace X by delta X amount. So if I project up now, these are the 2 new rates at the displaced point. And you'll notice that this one here is V1. So this is V1. and this one is V2. And what you'll notice under these conditions, V2 is greater than V1. Right? So if V2 is greater than V1, so V2 is greater than V1, that means I'm consuming X at a much faster rate. So X will continue to, well, X will start to decrease. So in other words, it starts to decrease and continue this way. If I did the displacement this way, I would find that now the curves have swapped over and V1 is greater than V2. And if V1 is greater than V2, then X must increase and it starts to migrate this way. So just from this simple graphical procedure, you can tell that this point here is unstable. So if I'm on this point here and I make a slight perturbation on either side, I'll either move to the lower one or I'll move to the high one. If I'm at one of the extremes, for example, this one, and let's say, and I displace myself upwards, okay, then I'll find that V2 is bigger than V1. If V2 is bigger than V1, that means X will start to decline. And so if X starts to decline, I start to return back to the steady state. Same happens if I try to displace downwards. This point here is actually stable. The same arguments apply here. If I displace up, it'll try to pull back down. If I displace down, it'll try to pull back up. So these two states are stable, and the middle one is unstable. Okay. So if I go back to sharing the screen, where did it go? So this is the diagram I had here. Okay. So the diagram I just drew is this one here. The red line is V2, and the blue line is V1. All right. And I think I have some additional figures here. Hold on, maybe not. Yeah, so this figure here shows you what happens to the displacements. If I displace at this point, if I displace this point, I get differences in the rate of change of X because the V1 is greater than V2 in this case, and V2 is greater than V1 in this case. Okay. So this tries to explain graphically why one of these is stable and two of these are unstable. All right. Now the other thing to note is that I can kill the instability by just changing the rate constant for V2. So let me stop sharing again. Let me draw that, that figure again. So I had this, I had that, and then I had that, all right? It's not a very good one, but okay. The slope here was K3. Now you can imagine, so here, actually I don't like that one at all. Let's start again. Let's do it again. Okay. I got to start from non-zero. So I'm going to put, that's the V2 with the slope K3. And then this, that's V1, okay, with the inverted sigmoid. What's interesting about this is that this slope here, actually K3, determines how many steady states there are. Because if I were to increase the slope, this line increases, okay? And if this line increases, I no longer have 3 intersection points, but I only have 1. So in fact, I've reduced this system to 1 steady state now, 1 stable one. If I decrease K3, I'll reduce this slope. And now, if I extend it far enough, the intersection point occurs here. Now I've only got 1 intersection. It doesn't intersect here or here. I only get 1 steady state as well. So, and that's what that diagram I just switched back from was showing. Let me just show you that again. Let me just show you this diagram I had here. So that's what this diagram is here showing. So in the middle, when K3 is 0.7, which was the setting I had for the simulations, we see there are 3 intersection points. If I increase K3 to 1.2, I only get 1 steady state, which is the lower one. If I decrease K3 to 0.26, I miss these 2 intersections out and I only intercept this high one here. So here I have 1 steady state, 2 steady states, 1 steady state, 2 states, 2 of which are stable, 1 unstable, and 1 state which is stable. So let me show you this then, given what I've just said. So I'm going to draw this again, okay? So we've got that line here, we've got this line here. What I want to do, what I'd like to do is to do a different plot where I want to plot on this axis X, just like this one. So on this axis, it's, on this axis is V1, V2. On this axis is X, okay? Now I want to plot X, but this time as a function of K3. So the slope here is K3, all right? So let's have a look at this situation where K3 is this value, and you notice I have 3 possible values for X. So at this value of K3, which might be here, I've got 3 values for X, okay? If I increase K3, all right, so increase K3, I've only got 1 value of X. So in other words, I'm somewhere around here. If I decrease K3, again, I've only got 1, I'm going to join them up here. I've only got 1 intersection point, which is the high one. So at a low K3, I have a point here. All right, so I've plotted here basically the intersection points. So that's the that intersection point. These 3 correspond to these 3 intersection points, and this one here corresponds to that intersection point. Now I could move K3 continuously. And as I move it continuously, I could record all these intersection points. And if I do that, I get a drawing, I get a figure that looks like this. I get this sort of, it's a 2, I guess. It's in the shape of a 2, all right? And these points along here mark all the steady states that this system admits as we vary K3, all right? So technically, this is actually called a bifurcation diagram. All right. And you notice there are these turns here, right, where the thing suddenly turns around. These are called turning points. Okay. Right, and there's one here and there's one here. So I could now do an experiment here. Let's say I started at a high K3 and I was here, okay? So that means I've only got 1 steady state. And I slowly decreased K3, all right? Let me change color. So I slowly decreased K3, all right? So as I decrease K3 slowly, I should follow this steady state line, all right? Now the question is, what happens here at this turning point? How's that? Is that not? Let me see. Maybe I should go over here a bit. So what happens at this point? So if I keep decreasing K3, what will happen? Well, it won't follow this line because I'm decreasing K3. In fact, what it does a jump. It does an abrupt jump, and it jumps to the high state. So this is an example where it's jumping from transitioning from a low state to a high state. As I continue decreasing K3, it then follows, this curve, all right? Now what happens if I start, so now I've reached a low K3 at a high X. Let's say I start here and I'll start moving upwards. So if I start moving upwards, I start moving K3 up, I start following this line, but I don't jump down here where I emerged before, but I continue following this line. And eventually when I get to this point, of course, I jump back down, okay? Now, this is an odd thing because the behavior of the system depends on whether I increase K3 or I decrease K3. So it's not the actual value of K3 that counts, it's whether I'm starting from a low value and increasing or starting from a high value and decreasing. Depending on which one I do, I get a different route, all right? And this idea where you get different routes depending on where you start from is called hysteresis. It comes from the physics field. We look at magnetic fields. But the idea is that there's a sort of a memory, the system has a sort of memory where it remembers that it came from a higher value of K3, and therefore it takes this route, whereas here it sort of remembers it starts at a lower value of K3 and it takes a completely different route. I mean, that's a bit of a stretch of an idea, but anyway, they've taken the same terminology and called it hysteresis. Okay, so how can we reproduce this in a simulation? So let me share the screen. Okay, and we bring up a simulation here. Okay, so let me go to a new simulation. It's not that one. It's, where are we here? It's not that one. Where is it? Oh, there it is. Okay. So what I'm going to do, I'm going to comment this out, okay? So what I've got here is exactly the same model, no change in the model, okay? So what I'm going to do is I'm going to start x at a lowish value of 1, and I'm going to run 70 time course simulations. And well, for each one, I'm going to run a simulation from 0 to 10, and I'm going to pick the steady. So I'm going to, if I run this from 0 to 100, I'm likely to reach a steady state, okay? I mean, I could run it for 1,000 if I wanted to make sure, but I want to make I'm assuming that after 100 time points, I've reached steady state. At that point, I'm going to record X, and I'm going to record K3, and then I'm going to increase K3 by a small amount, and I'll do it again, okay? So I'm going to collect values of K3 and values of X in these two arrays, or lists rather, and then I'm going to plot them. So let me run this and we'll see what we get. All right, so this is the effect of increasing K3. So I'm increasing K3 from a value of 1 to a value of something like 1.6. So, and look what you see. You see it's this line represents the steady state solution, all right, as a function of K3. So we start off at a high steady state, and as K3 increases, we slowly decrease, 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 and then we get this abrupt jump down, and then it continues up. If I increase the number of points, and then we might get a even steeper. Yeah, it pretty much becomes vertical.
Sure you do.
Right, and that reflects. Do I have this picture here? I think I have somewhere. Hold on. Yeah. So that reflects what's happening here. So although I think the curve is the other way around here, but that doesn't matter. So what I'm doing, oh no, it's correct, it's correct. So this is the high point, all right? So as we increase K3 and following the high point, and at this point here, it just jumps down and carries on up. This is exactly what we have here. Now I can start decreasing K3 as well, and I should get a completely different curve. So, and that's what this commented code here is. So this one now starts from where K3 was, which is at a high level, 2.25. Then I start decreasing K3, and I'm running simulations at the same time. Okay, so let's run this. Not enough points. Let's put that up, 200. Got to match the other one, 0.1. Okay, so there you have it now. So the other curve is in orange, and you can see so it's K3 is decreasing. We're following the steady state. Once it gets to this point here, it then jumps up and then continues following the steady state up. So this is exactly this diagram, all right? But now done with a simulation. So you may be asking, what's happened to the middle bit, right? This dotted bit here, this blue bit. Well, that bit is unstable, and that's the middle steady state, and it's unstable, and I can't get to it via a simulation, right? I can't get to it, and so it misses it out completely. But it is there, actually, it is there, and if you could compute the unstable steady state, using the steady state function. If you did that, you'd actually be able to find the points, and it does, it'll do some kind of a 2 shape, all right? But we can't see it here because we're doing a time course simulation, and it never gets to the steady state. All right. So the next question I want to ask is, what are the conditions under which we see bi-stability? All right. So under what conditions do we see bi-stability? And so let me start. Yeah, so let me just remind you what the values for the elasticities are. Remember, these are the sensitivities. For first order, it's 1. And if it's sigmoid, it's greater than 1. Okay, so let me just stop sharing for a minute, and I'll put it on a piece of paper. So remember the elasticity. So this is the scaled one now. Okay, the scaled one is dV ds times S over V. Okay, if it's linear, the elasticity is 1. All right. If it's sigmoid, the elasticity is greater than 1. Okay. All right. So we need to remember that. All right. So let's go back to the algebra. Let me go back to sharing this thing again. All right. Oh, so let's do a stability analysis on this simple feedback system. So what we have here is the stoichiometry matrix. It's just 2 reactions, 1 species. Okay, so the stoichiometry matrix is 1 minus 1. These are the unscaled elasticities. There's only 2. Okay, x on V1 and x on V2. To get the stability, we have to compute the denominator, or the determinant of the inverse of the Jacobian. All right, so this is the Jacobian inside here. Then I take the inverse and I need the determinant. And if you multiply that by that and subtract it from S1, this is the determinant you get. All right, it's actually quite simple. This is the characteristic equation. What we need to know is under what conditions is S negative? Because if S is negative, which is a root, if X is negative, we know it's stable. All right. So to make things easier, I'm going to convert everything to the scaled elasticities. And remember, we had this relation last time. So the unscaled elasticity is just the scaled one times V divided by X. All right. So I'm going to take each of these these funny epsilons, and I'm going to swap in one of these. Okay. So if I do that, I get this. All right. So that's all I've done is I've just swapped the squiggly epsilon for this smaller epsilon. All right. Now I know at steady state V1 is V2. V1 equals V2. All right. So these 2 ratios are actually identical, and I'll call this ratio F. All right. So I'll rearrange this equation. I'll get the root onto one side, so that and then I can pull the V2 over X and V1 over X out as F, and I end up with a difference in the 2 elasticities. All right. Now I know that F is greater than 0 because I know the reaction velocities have to be 0, and I know the concentrations have to be 0. So F must be 0. So for stability, the root must be negative, which means that the only way to get S negative is for this to be negative. Therefore, for stability, this has to be negative. Okay. Now, let's recall that this is positive feedback. So this elasticity here must be positive. All right. This elasticity is also positive because it's the forward rate on the mass action rate law, V2, but I got a minus in front. So if you look at this, long enough, you'll realize that for the system to be stable, the feedback elasticity must be less than the forward mass action elasticity. Now, since the V2 is a mass action rate law, its elasticity must be 1. So in other words, for bi-stability, the feedback elasticity must be greater than 1. All right, so that's basically the rule. So if the feedback elasticity is greater than 1, we'll have bi-stability. Now, of course, we can get bi-stability by using sigmoid kinetics, because I just said that with sigmoid kinetics, the elasticities will be greater than 1. And so this is the condition. In fact, you can have all sorts of combinations here. You could, so long as this condition is met, you'll have bi-stability. All right. And so the final conclusion, then the condition for instability, assuming first order kinetics on V2, is that this one must be greater than 1. And of course, this is easily achieved by having, if the positive feedback displays sigmoidicity or cooperativity. All right. Okay. Let me stop sharing. Let me see if there's any questions. Any questions from anybody? You can type your questions in as well, or you can just talk. All right. Okay. Okay, and this just follows what I just shared. There's There is special software that's available for plotting these what are so-called bifurcation plots, which I won't go into, but this one's plotted by something called SPW Auto C# tool. They can be a bit tricky to use, but they can be a bit temperamental at times, but you can use them to compute these bifurcation diagrams. Okay, and we've seen that. Okay, so here's some tricks you can do now. So there's a thing called irreversible bi-stability, and this may actually be something that the differentiation circuits use when differentiating cell types. Because you'll notice that, you know, for this one here, right, I can actually freely jump from the high one to the low one. You know, if I'm at the low point and I inject enough X, I will jump up to the top one, okay? And if I manage to remove X, I can also jump down to the bottom one. So this isn't very good if you want to use this for controlling differentiation, because you can imagine, let's say a cell differentiates into a liver cell. If you're not careful, there could be a random event which forces the change in the X value, and it suddenly jumps back down, and it de-differentiates. Right? So, but we don't see that. Liver cells stay as liver cells, and neuron cells stay as neuron cells. They don't flip about from cell type to cell type. So there must be some way of locking these bistable switches in. And one way, although it probably may not be the way that's used in biology, but one way is to use this thing called an irreversible bistable system, and that's actually quite straightforward. Let me show you the bifurcation diagram first. So what's happened here is the bifurcation diagram has been basically shifted to the left. All right, so the whole thing has been shifted to the left, so it straddles the zero point. Now, this x-axis is some kind of signal. Let me go to the pathway that did this. So this is the little pathway that resulted in that plot. So I have a signal coming in here. It causes production of R1. R1 gets degraded, but R1 also activates this cycle, and this cycle then feeds back onto V1. In fact, this is a positive feedback here. So if I plot, I think it's R1 versus signal, okay, so it's R1 versus signal, I get this. And you can arrange the parameters so that the entire S-shaped curve is shifted to the left. So it now straddles the zero axis. Now, the signal is a molecular signal, and molecular signals can't go negative. That means it's impossible for the signal to go below zero. In other words, this piece of behavior that's sticking out here into the negative quadrant is inaccessible. You can't get to it. So imagine this. Let's imagine we start at a low state and we start increasing the signal. We increase. We get to this point, we flip up to the top. So now let's say this is a differentiation circuit. The switch flipped, and it's now differentiated to maybe a liver hepatocyte cell.
Dr. Sorrow.
We can remove the signal
Hello?
now, and everything's fine. Because if I remove the signal,
Do you copy?
let's say I slowly decrease the signal, it starts dropping, and that it stops at that point. I can't reduce the signal below zero because this is a
Dr.
molecular
Sorrow,
signal.
sorry.
I can't have negative concentrations. So essentially, I'm stuck at the high point.
Dr.
So
Sorrow,
now it doesn't matter what I do to the signal, I'll stay at the high point.
we can't see your
You can
screen.
imagine maybe this is could be used perhaps to lock in a high state. I suspect what's happening in cells also that there are changes to the DNA
Herbert.
to actually remove the action of the signal completely, or to do something anyway. Or it may even remove the bi-stability once it's in the high state, and then there's no way that you're going to drop down to a low state and de-differentiate. All right. Now, there are many other designs you can do. This is a famous one. It's called a toggle switch. This is also bi-stable. This involves two nodes, not just one. Remember, up to now, we've just had one X, right? But you can have two of them. You can have one node inhibiting the second node, and the second node inhibiting the first node. And this is called a toggle switch. So let's say S1 is high. So if S1 is high, it represses S2. So S2 is low. And since S2 is low, it's not repressing S1. So this is one of the stable states. And then the other one is when S2 is high, and that represses S1. And since S1 is repressed, there's no repression of S2, and so S2 is stable. And you can flip back and forth on these. For those of you who do any electronics, who know flip-flops, this is basically how a flip-flop works. All right. So flip-flops in electronics are often used for storing, bits of information. It's pretty straightforward to build one of these toggle switches. You can just have two Hill-like equations that repress each other. That's just a degradation reaction on each one. This thing will behave as a bistable system. Okay, and yeah, there it is actually built. These are also easy circuits to build if you're a synthetic biologist. So we have two genes. First gene inhibits the second gene, and the second gene inhibits the first gene, and that's all there is to it. So Will is requesting control of your camera. No, you can't have my camera. Okay. All right. So that's all I want to say about bistable systems. Well, no, actually, I do want to say a bit more about bistable systems. We're in a different context. Are there any questions at this point? Could you please project your screen? Does my screen disappeared? Can somebody confirm they can hear me? We missed the last 7 minutes or so. We can hear you. Somebody, I wonder if what happened to the screen, I wonder. Do you have my screen now? No, the video is running.
You guys, there's a kitchen.
You see, I'm showing my desk at the moment. So what do you actually see?
We see your desk right now.
So what do you actually see? It's just a black screen?
So right now we see your desk, but earlier when you were talking about the code you were running.
You should see my desktop at the moment. Okay, all right then, okay. Yeah, I switched off sharing because I wanted to go back to the desktop. So did you see, I'm sharing the desktop now. I'm sorry, I'm sharing the screen now. Did you see this piece here?
No.
Unfortunately, I can't see the chat while I'm sharing. Hold on. I can't see the chat while I'm sharing my screen. Oh, here we go. Hold on. Oh, here we go. Yeah, I can't hear you at all. Yeah, I can't hear you at all. I wonder why. That's strange. You didn't see it before. All right. So did you see this piece? No. Oh. Did you see this piece? Okay. All right. Did you see this? You didn't see this bit either? Oh, you saw this bit. Okay, good. All right, then. So you saw the bit about stability. I'm going to unshare the screen, okay? Yeah, you should be getting sound. I mean, I should be hearing you. I don't know why I'm not hearing you. Which is very strange. Okay. All right. All right, so the irreversible bi-stability. So this little circuit here, if you were to build this little circuit or run a simulation, you'll get this kind of bifurcation plot. As I was saying, what's unusual about this one is that the entire S-shaped curve has been shifted to the left. And so that it straddles the zero axis line. So the x-axis is the signal, okay, and R is the output. And the signal is a molecular signal, so it can't go negative. So I can only take the signal from 0 to 3 I can't take it to -1, right? That's physically impossible. And because the entire S curve has been moved to the left, this whole chunk here, right, this whole chunk here, I want to ask you one question. Can you see my cursor? Can you see my cursor? Yes, okay, good. So this piece here that protrudes out is inaccessible. So you can imagine that if I started off at 0 signal and started increasing the signal, we'd follow this red line here. And eventually we get to this turning point and you flip to the top. Now, there's actually no way now to get to the low steady state, because if I decrease the signal, I start following until I hit the x-axis and I can't go any lower. And so I can't flip down. So you're sort of stuck in the upper steady state, all right? And so this is called an irreversible bistable switch. It's simply because physically the signal can't go below 0. So you can do various tricks like this. And as I was saying, this is one possible way that you could lock in a cell after it's differentiated. So you'll have a signal that signals the cell to differentiate, but then it can't undifferentiate because it doesn't matter what you do with the signal, it just stays in the differentiated state. And this is sort of the case that's happening here. So once it's in the high state, it doesn't matter what I do to the signal, it'll stay in the high state. Okay. And then I mentioned, I mean, you can build all sorts of things like this, but this is a toggle switch. There's also a positive feedback here. It may not look it, but 2 negatives make a positive. So there's actually a positive feedback going round 1 cycle, okay? Each of these is negative, right? But together they form a positive feedback. And this is a toggle switch. You can either have S1 high and S2 low, that's stable, or S2 high and S1 low, and that's stable, all right? And it's pretty easy to build a model of this. You can use a hill-like equation that has repression and then 2 degradation steps, all right? All right, so that's basically all I want to say about in this chapter anyway, chapter 23. Let me just summarize what we did just very quickly. Let me go back. So we had a quick picture of a system with positive feedback. Then there was a little computer model we had. I ran that, showed you that you can get, depending on the starting condition, you can end up with different endpoints. And this showed us that this system had at least 2 steady states, and in fact they're both stable. But unknown to us, there was actually a third, which is straight down the middle, which is unstable. And then we plotted the 2 rates versus x. You can see this pattern, and where they intersect, those are the steady state points. You can see here immediately there are 3 steady states. The middle one is unstable. The 2 on the ends are stable. And I noted that the line here has a slope k3. If I move the line, I can switch from 1 steady state to 3 steady states to 1 steady state, okay? And if I plot the intersection points as a function of k3, I will get, hold on, I will get, wait for it, I will get something like this, right? So this just plots the intersection points on the y-axis and the value of k3 on the x-axis. And these are all the steady state points. And here we have the unstable one here, stable here, stable here, okay? Then I noted you could work your way around the loop by increasing k3, then decreasing k3, and you can do this loop all the way around the steady states. All right. And then we have the irreversible bi-stability. Okay, so the last thing I want to do is a little bit on, just one more bit on oscillators. So last week and the week before, we talked about one kind of oscillator, which was this negative feedback oscillator. I'm going to unshare now, okay, so don't panic, right? Stop sharing, all right? So here we are. So we had this oscillator, which looked something like this. Oops, that's S3, and it had a negative feedback going all the way back there. All right. This is a negative feedback oscillator, also called a phase shift oscillator. And it's called that because, you know, the phase shift is critically important to make this thing oscillate. All right. Now, if I go on, if I look up, actually, I'm going to share the screen again. If I go to Google, right, and look up phase shift oscillator, what you'll find is our electronic oscillators. And here's, let me see, let me get a transistor. There we go. Here's a nice, this is a transistor one. Oops, here we go. Oh, go away. So if you look at phase shift oscillator, you'll see things like this. So this is actually exactly the same as the pathway one. These capacitors here represent the phase shifts. They'll do the phase shifts, all right? So they represent the three species, S1, S2, and S3. The transistor just represents the amplification process, and then it feeds that back to the first capacitor, right? So you'll get phase shifts here, and as long as you get up to 180, and this one does a final inversion, this thing will oscillate, all right? So this is a classic electronics phase shift oscillator, and you'll see lots of them. So if you look this up, you'll see there's loads of them. You can either run them off a transistor, like I just showed you, or you can run them off an op-amp like this. So the final stage is there just to do the inversion and the amplification, and then the capacitors are there to do the phase shifting. All right. So now the thing about phase shift oscillators as well, you tend to get nice. It's easy to get nice sine waves from it. All right. So it's one of the characteristics of a phase oscillator are nice sine waves. It's much harder to produce things like sawtooth waves or pulses or things like that. It's not suited for that. And for that purpose, there's a completely different kind of oscillator called the relaxation oscillator. I should stop. I'm going to stop sharing the screen now, right? Don't panic. It's called the relaxation oscillator, and this is what I want. This is the last thing I want to talk about right before we leave. So relaxation oscillator. Let me show you a relaxation oscillator. Let me just flip to share screen again. Sorry, I keep flipping back and forward. That's how it is. This is a YouTube video. If I run this, there it goes. Flash, flash, flash. This is a relaxation oscillator. Very easy things to build. They're less complicated than phase shift oscillators. But the question is, how do they work? So let me stop that for a second, and let me go to this page. So this page is the actual circuit that YouTube video actually showed. And what we have here is a strange arrangement, but what we have here is a transistor that's connected the wrong way around. Okay, there's no connection to the base. All right. So when I say the wrong way around, the collector's at the negative end and the emitter is at the positive end, right? Normally you do it the other way around. But the transistor is connected to an LED. So we're not using the transistor here in the way you'd normally use a transistor. It's not been used as an amplifier. It's actually been used as a voltage threshold device. So when the voltage across the transistor gets to a certain value, you get a breakdown voltage and it starts to conduct. And when it starts to conduct, it lights the LED. All right. So the emitter then is connected to this point here. So this is the voltage then that controls whether the transistor will switch on or not. This voltage here in turn is controlled by this resistor capacitor circuit. So let's imagine everything is off and we connect the battery. So what happens first is the voltage here this basically is almost a through circuit because the capacitor just starts to charge. So there's current, quote, flowing through here, unquote. It's not really flowing because it's a capacitor charging, so there's a gap there. But anyway, what it does mean that there's the voltage here is quite low, right, because it's charging up. As the capacitor reaches a full charge, this voltage starts to rise at this point. Once that voltage starts to rise, you get a breakdown of the transistor and it starts to conduct. When it starts to conduct, the LED lights up, but at the same time, the capacitor discharges. And then the breakdown voltage is no longer there, and the transistor turns off, and then the capacitor starts to charge again. And so it goes round and round like this. Okay, and this is called a relaxation oscillator. Right. Okay. So that's your classic negative feedback oscillator. Okay, with the phase shifting and the negative feedback. What about a relaxation oscillator? So these are slides you can grab off the Wikipedia page on relaxation oscillators. These are my slides from some years back, actually, on another course, and somebody grabbed them and put them onto Wikipedia. But let me show you this. Okay, so this here is a simple bistable system. S0 is fixed, X1 is fixed, and I got a positive feedback here. This will behave just like we've seen before. It'll show that S-shaped curve. It has two stable states, one unstable one. So now let's do something really simple. Let's just stick an extra reaction onto S1. So we'll now release S1. It can now float about, okay, and I'll stick an extra reaction on the front. Amazingly, just by doing this simple modification, this thing starts to tick like a clock, all right? So just by adding this extra step here, it starts to oscillate. That's all it took. And what we have here is something very similar to that transistor circuit. So the voltage that controls the quote transistor is S0. The transistor is this middle step, all right? And that either turns on sharply or not, depending on the presence of S1 and whether S1, activates starts the reaction going or not. When the reaction, so maybe let's walk through this and show you how this works. So let's say everything is empty, okay? So everything is empty, but X0 starts to make S0, S0 starts to make S1, S1 starts to build up. At a certain point, the bistable switch flips on, so this rate suddenly goes high, and in the process, it pulls S1 down, and when S1 gets pulled down, it turns the reaction off, and it flips to the low state. And then it starts charging up again. So this will charge, discharge all the time. And this is why you get then this oscillation. Now, what's characteristic about these oscillations is that they're spiky. And they're spiky because they tend to have two time scales in them. One time scale is concerned with how long it takes for S1 to charge up or how long it takes for the capacitor to charge up. And one time scale that flips the state from high to low. All right, and that's a fast process, and so you get a mixture of fast processes and slow processes, and that's why then you get this spikiness. So the spike is the fast process, and then the slow slope is the slow process. All right, so you get these, and so most signal generators, electronic signal generators, are built on relaxation oscillators. So how does this work in terms of the bistability? In terms of the bistability, I can plot the bifurcation plot just for the bistable portion, right? And this is my S-shaped curve, all right? And the input here is S0, and the output is S1. So what's happening here is, let's start at low S1. So at low S1, we're in the low state. So S1 starts to accumulate, and as it starts to accumulate, we start to move up this line. But eventually we reach this turning point, and it flips to the high state. Now, once it's in the high state, the rate is much higher. And because the rate is much higher, it consumes S0 faster, and so S0 starts to decline. And as it declines, it follows this black line here, then reaches this turning point, and flips to the low state, and we're back to square one again. And so this thing just goes round and round and round this bistable switch. And that's basically the relaxation oscillator, okay? I've tried to show you in the diagram that there is actually a negative feedback. There's a positive feedback here, and there's actually a net negative feedback going around there. So a relaxation oscillator has one positive feedback, and one negative feedback. So that's how you build a relaxation oscillator: one positive feedback and one negative feedback. Let me see if I go, oh yeah. And so sometimes you'll see it depicted like this. If you have two nodes, so there's positive feedback on one of the nodes, and there's a long range negative feedback via the other node, okay? The other thing about relaxation oscillators, which is nice, is they only require 2 variables, S1 and S2, whereas a feedback oscillator requires 3. And it turns out that the cell cycle, that controls cell division, at the heart of that oscillator is a relaxation oscillator. In fact, there are all sorts of ways you can build a relaxation oscillator. I put together this list in a review I did some years ago. You can design them in all sorts of ways to build, and so it's quite a flexible way to build an oscillator. Maybe that's why evolution picked the relaxation oscillator to control cell division, or maybe it's because you wanted 2 different time scales, one or the other anyway, or both. I don't think there's anything else other than to say people have built relaxation oscillators using synthetic biology, but I'm not going to go any further on that one. I think that's it. Yeah, I don't think I want to say any more. So there's a section here on relaxation oscillators, which you should read. It's in chapter 24. Shows the spiky oscillators there. Has a little model that shows it off. And then I talked a little bit about oscillator classification. There's relaxation oscillators, there's feedback or phase shift oscillators. Those are the 2 groups. And they have different characteristics. One has 3 variables, one has 2, one is spiky, one is more sinusoidal, so on. Okay, I think that's it. Yes, I think we've reached the end. So let me switch off sharing. Let me point myself, but I'm upside down. Let me flip over. Oops, sorry, I didn't want to do that. Let me flip over. Here we go. So are there any last questions for you? So your quiz plus is on Thursday. I'll send it out on 9 o'clock on Canvas. You can submit your PDF doc or scanned in answers onto Canvas, and we'll grab them from there. It's not an ideal solution, but that's what we'll do. You'll have it for about 10 hours from 9 o'clock to 8 o'clock. I've given you time because I know you might be doing other stuff as well. Shouldn't take you more than an hour to do the quiz. It's not going to be as long as the midterm, so it should be all right. And as I said, I gave you the list of topics. Don't include stuff we've done up to this point, okay? Including relaxation oscillators and bi-stability. So, any questions? It's funny why you can't speak to me. Hold on, maybe let me try this. No, can you speak to any? No voices. No. I'm not sure why. What is the way to the quiz going to be? That was a good question. I mean, it's not as big as what the final exam was going to be, so it's probably going to drop a bit. Let me see, let me just go to Canvas and find out what it was originally. Hold on, I'm getting in now. Just go to the syllabus. There we go. Let's see, it was 30. So I think we should drop that. We should probably drop it to at least 25. Okay. So the contribution from the final will be no more than 25. The chapters for the quiz, there's a link on the website, or there should be. You should have got it. You should have, oh, here we go, yeah. Oh, no, you should have got an email. You should have got an email which listed all the chapters that will be covered in the quiz. If not, I'll send it out straight after this again. All right? But you should have it in an email. Anything else? I'll be in tomorrow between 9 and noon, so if you want to pick up anything, I'll be in my office. Anything else? Looks like no. I'll upload this video as well after this too. So I sent out a bunch of rules yesterday. One was you can use whatever resources you want to do the quiz, anything online, whatever. What you're not allowed to do is collaborate. Now, of course, I can't enforce that. So I'm going to have to trust you that you won't. I mean, obviously you can talk to each other, but just don't talk about the test. I'll try to avoid talking about the test. All right. So do the honorable thing, okay, and not collaborate. All right. But other than that, you can use whatever resources you can find online, and you can use things like Wolfram Alpha if you want to, anything like that. Okay. Anything else before I sign off? Because we've only got a few minutes. I don't know why why you can't talk to me. Hold on, let me try now. Somebody say something?
Can you hear us now?
Oh yeah. Except it's coming out in a strange place. Say something again?
I'm coming out of a strange place.
Say it again?
I'm coming out of a strange place.
How odd. It's coming out of the computer speaker. Huh, strange. Okay. Let me try speakers. Okay, hold on for a sec. Try speaking now.
How about now? Where's it coming from?
Hmm.
Hello, can you hear
Yeah.
me?
Oh, I know what it is. I'm sorry, ladies and gentlemen. It's my fault. I turned the volume down. So now you can say whatever you want.
Thanks, Dr. Sorrow.
I had to turn the volume down because there was a huge racket upstairs this morning. No, oh, okay. So sorry about that. So any questions from the 10 of you that are left? All right then. See you tomorrow morning if you want to pick up your midterm, whatever. Other than that, Thursday, 9 o'clock, I'll issue the quiz, okay? We good?
Dr. Sorrow, I have a question.
Oh yeah, good, yeah.
Can you explain the scaling you did at the beginning of this lecture
Yes,
with the elasticities?
I can. It's this bit here. So we did the scaling before, but let me just, it's this bit here, right? Oh, not sharing, right, here you go. It's this bit here, all right? Yeah, correct?
Yes.
Yes, okay. So now, of course, the transfer function is in terms of these unscaled derivatives, okay? Because we've linearized, so we get these dv by dx's, okay? And these are expressed using this this big epsilon, right? So these are just the derivatives dv by dx, okay? Now you have to remember that the scaled elasticity is the unscaled scaled. So what I'm then going to do is I'm going to turn those equations around so I can express. Hold on for a second. I can annotate here. So I can express the unscaled one in terms of the scaled one now and the scaling factors, right? So does this equation make sense first?
Yes, that does. Thank
Okay.
you.
All right. So all I'm doing then, every time I see one of these, like this one, right, I put in one of these. Okay. That's all I'm doing. I'm substitute each one of these for one of these. So when I do that, hold on, I have to switch this off. When I do that, I get this. I get this. All right. So I've just swapped the big epsilon for the little one with the v divided by x. Does that bit make sense?
Yes, it does.
Okay, and then I make the assertion, which is true, that v1 equals v2 because at steady state they must be the same. All right, and since obviously both x's are the same, these are common factors. All right, I'll call this common factor f. So I'll pull f out. All right, and I'll just rearrange it so I get s on one side and these two on the other side. And I know that f is positive because the rates are positive, x is positive, so the ratio is positive. So I know f is positive. Hold on. So I can then make, let me clear that. Hold on. Clear. Where's clear? So then I can make this assertion then. All right. And the other thing I can say is that this value here is 1 because it's a simple mass action. It's not a very good one, but that's a 1. It's a simple mass action reaction, so that must be a sensitivity of 1. And so this is then the condition for bi-stability. All right. So long as the positive feedback is stronger than the degradation sensitivity, we'll have bi-stability. That's a very simple condition then. All right. You okay with that? If not, email me.
That makes sense. Thank you.
Okay. All right. All right. So any other questions here? Nothing else yet. All right. All right. I'll let you go then. All right. So good luck. Been good fun teaching you, and I'll probably see you around next term, assuming the virus hasn't got us, of course. Okay. Bye now.